All right, everybody. In the last part of our notes here on section 8.1 that I want to go through with you guys are a little extra thing that I like to spend some time on that not every geometry teacher does. So if you want to skip this, you probably could, but I think it's going to save you guys some time. It's something cool called Pythagorean triples. And what a Pythagorean triple is a group of three numbers, hence the triple, that are all integers for which the Pythagorean theorem works on those three integers. So the first one we've got for you here is what's called a 3, 4, 5 triple. And everybody, these are not subtraction signs. I probably should write them with commas, 3, 4, 5, like that. I've just always written them this way. What that means is that it is possible to have a right triangle here, everybody, with side lengths of 3 and 4 for your legs and 5 for your hypotenuse. Let's check that real quick. So the Pythagorean theorem, as we've been saying, I like to write, is legs squared plus legs squared is equal to hypotenuse squared. And we believe this is going to work if one of our legs is 3, the other leg is 4, and the hypotenuse is 5. 3 squared is going to get us 9, 4 squared is 16, 5 squared is 25. And sure enough, if you go to simplify this left-hand side, 9 plus 16 is 25. And you end up with a group of three numbers here, 3, 4, 5, that the Pythagorean theorem works on. So there are 5 of them, usually, everybody, that we ask you guys, in the old days to memorize. For now, just ones you might want to write down and have handy. And I'm going to show you in just a second here how these end up being useful to you. Now, let me be clear. These are not the only 5 Pythagorean triples. There's actually an infinite number of them, and they kind of follow a pattern, except for that 4th one, which is kind of a weird one unto itself. But like I said, these are the 5 smallest ones in terms of the size of the numbers, so these are the ones you might want to have written down. So, how can we use them? Well, this is a problem right here, guys, that we could have done using the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. But this is really the best case scenario. You will notice that we're looking at a triangle right here with a leg of 9, an unknown second leg, and a hypotenuse of 41. Well, the best case scenario is that the triangle you're given matches one of these 5, and that's exactly what happens right here. Our third triple is 9, 40, 41. So now that I see that this leg is 9 and this hypotenuse is 40, guess what, guys? Excuse me, the hypotenuse is 41. That means that your second leg is going to be 40, and we don't really have to do any work on that. Now, I've been showing you guys this for a while. I always like to verify that just by doing, it went to sleep on me, hypotenuse squared minus leg squared minus the other leg squared. And sure enough, that gets us exactly 0. So yeah, we know that this one is right. Okay, so that saved us a little bit of work. Now, how about this one, though? There's no Pythagorean theorem, Pythagorean triple in that list we wrote down that had a 15 and a 39 in it. But in certain cases, definitely not always, but in certain cases, some things still tend to work out for us. Let me show you what I mean. You'll notice that 15 and 39, everybody, have a common factor. The biggest number that can divide out from both of those is 3. So with my little method, what I like to do is put a 3 in the middle of that triangle and circle it. That's our GCF. And now what we're going to do is divide that 3 out from each of the 2 numbers that we were given. 15 divided by 3 is 5, so I like to write that inside the triangle, but next to the 15. 39 divided by 3 is 13, so that's going to go right here. And now, if we focus on the purple numbers, there's a leg of 5 and a hypotenuse of 13. That is a 5, 12, 13 Pythagorean triple. So, what's missing is the 12, but you got to be careful about where you put that. The 5 and the 13 are written inside the triangle, so I'm not saying that x is 12. I'm saying that this little piece right here, I would write a 12 out on the outside. And now, to figure out the value of x, take a look at what's going on. You multiply from that inner number out. So 3 times 5 is going to get you 15. 3 times 13 is going to get you 39. So to get x, we're going to multiply 3 times 12 and find out that x is equal to 36. Now what we've effectively done here, guys, we've created similar triangles. there's the big triangle we're dealing with, which we believe was 15, and we think this x is 36 and 39, that being your right angle. And what we effectively did is we came up with a much smaller triangle that was exactly 1/3 the size of it. And this triangle here on the left, triangle number 1, is similar then to triangle number 2 here, which was the triple of 5, 12, and 13. So that's the little method with Pythagorean triples that I like to use there. All right, I think I'm just going to do that one with you here, guys. Let's get into the last big concept we have in this section, and that's Theorem 8.2. This one, everybody, is the converse of the Pythagorean theorem. And we didn't spend as much time on this concept this year as we have in other years, but a converse of a theorem effectively just reverses it. So let's talk about what's going on. Basically, the Pythagorean theorem says if your triangle is a right triangle, then leg squared plus leg squared will equal hypotenuse squared. The converse of the Pythagorean theorem flips that around, and it says if, and I'm going to go ahead and use the A's and the B's and the C's here, and you'll see why pretty soon, and it actually has 3 parts to it, guys. The first part says that if c squared is equal to a squared plus b squared, then, well, what do we know? Then triangle ABC must be a right triangle. So I'll go ahead and write that out here. So if c squared is equal to a squared plus b squared, and again, there's a reason I'm writing it with the c squared first, then we know that our triangle is right. So let me stop you right there. The type of problem we're going to be looking at here is going to ask you to use this word classify. So classify the triangle with sides of 11, 60, and 61. So the smallest of the 3 sides we're going to call A. The middle side is going to be B, and actually these two don't really matter which one is which, but what is important is that the longest side is C. And we're going to try to set up this connection right here, C squared, and then there's going to be some relationship that goes in this red box. I'll get to that in just a second. A squared plus B squared over here on the right. So in this problem, our C value is 61, our A value is 11, and our B value is 60. And again, I don't know what goes in this box yet, so I'm just going to leave it blank. And now, let's go ahead and evaluate each side of this expression. On the left side, or I should say of the equation, on the left side, 61 squared gets us 3721. So, okay, 3721. I'll figure out in just a second what goes in that red box. And now how about the right side? 11 squared plus 60 squared. And that, let's just take a look, 60 squared equals, how about that? 3721 as well. What a coincidence. So, the question now is, what goes in the red box? Well, pretty obviously, 3721 is equal to 37 plus 21. So I'll just do that up the list right here. And what we're looking at here is this case where c squared equals a squared plus b squared. That's exactly what we just wrote down. And this theorem, the converse of the Pythagorean theorem, tells us that if c squared equals a squared plus b squared, then your triangle must be a right triangle. So now we would go ahead and say that because it was equal, this triangle with side lengths of 11, 60, and 61 would have to be a right triangle. Now, you might be able to guess from this point, everybody, where we're going next. There are 3 mathematical possibilities. We've covered one of them. C squared could be equal to a squared plus b squared. The other 2 possibilities are, no, not that c squared could be greater than a squared plus b squared. And a third possibility now is that c squared is going to be less than a squared plus b squared. And in each one of those cases, we get a triangle that is not a right triangle. And that means that it's either going to be acute or obtuse. And I want to try to talk about which one is which here without me just spoon-feeding you this information. So let me play with this example for just a second, and then also the next example. I think we'll be able to figure out which is which. So once again, I'm going to compare c squared to a squared plus b squared with these values of a, and B and C. So in this problem, C is 7. Excuse me. All right, our A value is going to be a 3 squared, and our B value is 5. So on the left side, 7 squared is going to get us 40. Nope. Ooh, that was ugly. All right, let's try that again. 7 squared is going to get us 49. And on the right side, 3 squared is 9. 5 squared is 25. That's a 34. So pretty clearly here, 49 is greater than 34. So we're dealing with a case here where C squared is greater than A squared plus B squared, not equal to. So this is definitely not a right triangle, but the question is it acute or obtuse? And I think we can actually answer that by looking at the next example. I'll come back and finish that one in just a second. Take a look at what's going on here. The side lengths are 5, 5, and 5. They're all the same. So if I set up C squared and then A squared plus B squared, our C squared is going to be a 5 squared compared to 5 squared plus 5 squared. We get a 25 here on the left, and on the right, a 25 plus 25 is going to be 50. So again, pretty obviously, 25 is less than 50. And now we're dealing with a case where C squared is less than A squared plus B squared. Now, if it seems like I'm in the exact same spot where I was in the last example, B, you're kind of right, although it's different. But I want you guys to realize what kind of triangle we're dealing with here. With side lengths of 5, 5, and 5, this must be an equilateral triangle. All sides are congruent if they're all 5. And if we think about this, we already know, or at least we should, that in every equilateral triangle with 3 congruent sides, it must also have 3 congruent angles. And since the sum of those 3 angles in any triangle is 180, and in this case they're all congruent, we would just take 180 and divide it by 3 and find out that each angle here has a measure of 60 degrees. Hopefully that's something you guys remember from back in chapter 4, that in every equilateral triangle, your 3 angle measures always have to be 60. Well, that's what's going on here. And with 3 angles of 60, acute, 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 we are dealing here with an acute triangle. So what have we learned here, guys? When C squared is less than A squared plus B squared, our triangle is acute. We can kind of use then process of elimination to say that when C squared is greater than A squared plus B squared, that is when we are dealing with an obtuse triangle. So let's go back and finish up this little table here, guys. The second case right here, when C squared is greater than A squared plus B squared, that is when triangle ABC is obtuse. That's what we learned from the second example. And now the third one here, when C squared is less than A squared plus B squared, that is when triangle ABC is acute. And I remember that from the equilateral case that kind of points me in the right direction. So these are the 3 ways you can classify a triangle based on how the converse of the Pythagorean theorem works out. And the reason I did this backwards, everybody, is because, at least to me anyway, it makes sense that when your symbol here is greater than, greater means bigger or larger, that means we're dealing with an obtuse triangle with a big or large angle in it. And when that symbol is less than, we're dealing with something small, that's when we're talking about an acute angle. And if we had done it A squared plus B squared compared to C squared, then those relationships would have been exactly backwards. They're not wrong, but you just might have a harder time remembering them. I think this is an easier way to do it. Greater than means obtuse, less than means acute, but of course that only happens if you put the C squared out in front. All right, guys, that's a wrap on 8.1. Let's give that homework a try and see how we do. Good luck.